Hello, today I'm going to give you a brief idea about introduction to electrochemistry. We have seen many materials, some of them are good conductors, some of them are insulators, some of them are semiconductors based on their electrical conductivity properties. Some of them are used to conduct electricity from one place to another place, and the other materials like PVC, bakelites, these are used for making switches, circuit boards because they are good insulators. Now, from where this electrical energy is coming from? There are many sources. As per thermodynamics, as we know that the conservation of energy is there. So that means we have to convert the energy into the electrical energy. And the source may be solar energy, wind energy, and in some case it could be a chemical energy. In case of battery, that's what we are doing. We are converting chemical energy into electrical energy. Now, in that modern technological world, without batteries, we cannot imagine anything. So it is very important to know the principles behind the energy conversions, what is happening inside a cell. The branch of chemistry that deals with the study of the electrical energy transport and interconversions of electrical and chemical energy is called the electrochemistry. Now, electrochemistry reactions are redox reactions basically. They involve transfer of electrons from one place to another place. So in today's lecture, we will learn about the electrical conduction as well as construction of cells and some thermodynamic principles involved in the electrical chemical reaction. So what is an electrochemical cell? In which the chemical energy has been converted into electrical energy and vice versa. So it consists of two separate electrodes which are in contact with an electrolyte solution. Electrochemical cells are mainly classified into following two types. One is galvanic cell, which is also called the voltaic cell, and the another one is electrolytic cell. Galvanic cells are those in which a spontaneous chemical reactions generates in electrical current. That is, it converts chemical energy into electrical energy. So it is commonly known as a battery. And that's what the picture of a galvanic cell, in which we are taking two different container. In one container, the right container is having copper sulfate solution and the copper rod is dipped into that. And in left container, we have zinc sulfate solution and a zinc rod is dipped into that. And both the zinc rod and copper rod, they are called electrode. They are connected by a wire. And the two solutions are connected by a salt bridge which contains an agar-agar gel along with, it's basically a gel type of matrix which contains KCl, yes, potassium chloride. And the right hand electrode is also called the cathode, and exactly reduction is happening in that right hand electrode. And the left hand electrode is called the anode, and exactly oxidation is going on in that left hand electrode or anode. We'll talk about the reactions in detail in the future slides. Now coming to what is electrolytic cell. Now lysis means breaking. That means by the help of electricity, if we do some lysis type of reactions, is called the electrolytic cell. And of course, as we are getting the help of electric energy, that means this particular cell is having a reaction which is non-spontaneous. That means without the help of another external source of energy, we cannot do that. We cannot run that cell. And this is what a picture of electrolytic cell. Look at this. The container is exactly called the electrolytic cell, but by the help of an external battery, we are doing this. That is why I said this is a non-spontaneous reactions which is happening inside an electrolytic cell. So this is the clear picture about the differences between galvanic cell and electrolytic cell. As I said this, the main difference I would like to look at you that here in galvanic cell, anode is negative, cathode is positive, and in electrolytic cell, the anode is positive and cathode is negative. And also I said that in case of galvanic cell, spontaneous reactions is occurs, and in electrolytic cell non-spontaneous reaction is occurs. So as in galvanic cell non-spontaneous reactions is spontaneous reaction is happening, so it does not require external voltage of source. And for an electrolytic cell, as the non-spontaneous reactions are happening, it requires the external voltage source. So now we are going to tell you a little bit more about the galvanic cell, which is also called the voltaic cell. I told you earlier. So at anode is negative, cathode is positive, and I said oxidation takes place at the anode and reduction at cathode. Now discharge of ions occurs only at cathode. Spontaneous reactions occurs. Flow of electrons from anode to cathode, and electrons leave the cell at anode and enter the cell at cathode. Flow of electrons generates the current, and we have attached a voltmeter to understand what is happening exactly. And there is a salt bridge. The picture is not clear properly, but there is a salt bridge also which connects the two solutions, as I told you earlier. We have already learned in school days, when a zinc metal strip is placed in a copper sulfate solution, the blue color of the solution fades and the copper is deposited. The zinc strip is red, the brown cast due to the following spontaneous chemical reaction. So this is the reaction happening during this particular observation. Zinc plus copper sulfate gives you zinc sulfate and copper. The energy produced in the above reaction is lost to the surroundings as heat. In the above redox reaction, zinc is oxidized to Zn2 plus and copper 2 plus is reduced to metallic copper. And as I told you that these are the half reactions which is exactly happening at anode and cathode respectively. The oxidation is happening at anode and the reduction is happening at cathode. So these are the half cell reactions, you can say, or half electrode reactions. So if we perform the above two half reactions separately in an apparatus as shown in that picture, some of the energy produced in the reactions will be converted into electrical energy. Let us understand this in a much more broad way, that the function of a galvanic cell by considering Daniell cell as an example. The separation of half reactions is the basis of the construction of the Daniell cell. It consists of two half cells. Look at that one. This is called a Daniell cell. Copper is dipped into copper 2 plus, zinc is dipped into Zn2 plus, and the right hand electrode is called the cathode, where exactly the reduction is happening. What is the reduction reaction? Copper 2 plus 2 electron gives copper. That's the reduction I said. You know, accepting electron is called reduction. And in case of left hand electrode, we are having that reaction, that zinc converting to Zn2 plus and 2 electron, which is a oxidation. So that's what the picture of a Daniell cell. Salt bridge is there in which we have KCl, and what KCl is doing, I will clear you that in the next 2 or 3 slides. Look at this. This is the oxidation half cell. As I said, reduction half cell, I already discussed these things. And if I join these two things, the zinc and copper strips are externally connected using a wire through a switch and a load, example voltmeter. So voltmeter is the key factor. So if I on that particular circuit, we will say that electrolytic solutions present in the cathodic and anodic compartment are connected using an inverted U tube containing an agar-agar gel mixed with an inert electrolytes, such as I can use KCl, potassium chloride or sodium sulfate. Now why potassium chloride, why sodium sulfate? Can I use sodium chloride also? Answer is no. Why? I will clear you that in the next one or two slide. So here it is written, the ions of inert electrolyte do not react with other ions. First of all, that's the criteria. That means potassium chloride should not react with the zinc sulfate or copper sulfate, because these potassium chloride based salt breeze are dipped into the solution. They are connected with the solution. Only what they are doing, they are carrying the charges. They are carrying the positive and negative charges. Now why I am using potassium chloride? Because the K plus and Cl minus has exactly the same migration power to conduct the electricity. The solution in the salt bridge cannot get poured it out, but through which the ions can move into or out of the half cells. When I switch it on, the electrons flows from zinc strip to copper strip, and this is due to the following redox reactions. So that's what the reaction is happening. I already told you several times. So in anode reaction, zinc is being oxidized, and in cathode, copper 2 plus is reduced to copper. Clear? Understand? So this is just a picture that after several times the zinc anode has been uh, give you a very thin wire like structure, because it is being reacted, it is being dissolved in the solution. And the if you look at the copper cathode after some time, so you will see that some more copper has been deposited on the copper cathode. Now coming to the salt bridge, what exactly the salt bridge is doing. These are some real-time picture of salt bridge. So electrolytes present in two half cells are connected using the salt bridge. So also we have discussed that whenever oxidation happens at the zinc electrode, you will find more Zn2 plus in the solution than in the sulfate 2 minus ion. That means the solutions becomes positively charged, and in the opposite way the solutions of copper 2 plus becomes negatively charged, because it has more sulfate 2 minus ions, because some of the copper 2 plus ion has been converted to copper. So because to maintain the electrical neutrality between that two solutions, we need the help of salt bridge. What salt bridge is doing, inside salt bridge we are using KCl, that K plus is carrying the positive charge and Cl minus is carrying the negative charge. That means their power of migrations of charges are exactly same. That is why we are using KCl. So if anybody asks you that what exactly this job of the salt bridge, the job of the salt bridge is to completion of the circuit, number one. Number two, to maintain the electrical neutrality. Now look at this. How can we give or write the notation of the galvanic cell? That's what we will understand here. We have already studied Daniell cell, but right now we will understand that how exactly we will write about a salt bridge, write about a particular notation of a reaction. Look at this. It is look at the left bottom corner. It is written zinc solid. So that means zinc, as well as we have to write their physical state in the bracket, solid. Then a single line. That single line stands for a phase boundary. That means change of state. That means zinc and Zn2 plus are not mixed with each other. They are they have a phase difference. The zinc is a solid and Zn2 plus is a solution. So zinc and Zn2 plus are having a phase boundary, and Zn2 plus and copper 2 plus are having connected by salt bridge. So that double line stands for salt bridge, single line stands for phase difference. So that's what is the notation of a galvanic cell. And exactly as I said, that the right hand electrode is called the reduction half cell, and this is what the cathode is. And the left hand electrode is oxidation half cell, and this is what the anode is. This is just another example. Okay, that's clear example where exactly it's happening, where exactly anode oxidation happening, cathode reduction happening, and that E naught for the linear cell is 1.1 volt. That's the standard electromotive force of the cell. Now look at this. This is just an example that what kind of questions may be asked from this particular section of the lecture. The question is given that if the net redox reaction of a galvanic cell is given below, that chromium is converted to chromium 3 plus and copper 2 plus is being converted to copper, then what will be the cell notation? The cell notation will be written at the last, that is chromium solid, then single line stands for the phase separation, then Cr3 plus in AQ. AQ stands for the aqueous, and you can also write the concentration of Cr3 plus here. Then a double line stands for that salt bridge connected with in between the two solution. Then we have copper 2 plus again, aqueous, single line, copper, solid. Understand? So now we will understand about the EMF of a cell. What do you mean by EMF? We have learned that when two half cells of a Daniell cell are connected, a spontaneous redox reaction will take place, which results in the flow of electrons from anode to cathode. So, if I want to define the EMF, let me tell you, the force of pushes the electrons away from the anode and pulls them towards cathode is called the electromotive force, or you can call it also cell potential. The SI unit of cell potential is of course volt. When there is 1 volt difference in electrical potential between the anode and cathode, 1 joule of energy is released for each coulomb of charge that moves between them. Understand? Like for Daniell cell, the cell voltage depends on the nature of the electrodes and concentration of the electrolytes and the temperature at which the cell is operated. For example, at 25 degrees centigrade or 298 K, the EMF of the below mentioned Daniell cell is near about 1.1 volt. How can we measure that electrode potential? The overall redox reactions can be considered as the sum of the two half reactions, that is oxidation and reduction. Similarly, the EMF of the cell can be considered as the sum of the electrode potential at the cathode and anode. Just I have written here. So here E ox anode represents the oxidation potential at anode, and E red cathode represents the reduction potential at cathode. So it is impossible to measure the EMF of a single electrode, but we can measure the potential difference between two electrodes using a voltmeter. If we know the EMF of any one of the electrode which constitute the cell, we can calculate the EMF of the other electrode from the measured total EMF of the cell by using the above expression. And that's how the reference electrode idea is coming. So reference electrode are those whose EMF is known to us. Like that, standard hydrogen electrode are one of those reference electrode. So what is that standard hydrogen electrode, or SHE? So it has been assigned an arbitrary standard EMF of 0 volt, which consists of a platinum electrode in contact with 1 molar HCl solution and 1 atmospheric hydrogen gas. The hydrogen gas is bubbled through that solution at 25 degrees centigrade as shown in this picture. So SHE can act as a cathode as well as an anode. The half cell reactions are given below. If we consider that SHE in the cathode, then the reactions should be written in the form of reduction, that is H plus electron gives H2. But if we want to consider that in anode, that means I have to write that H2 minus electron becomes H plus. But in both cases, the standard EMF of these particular hydrogen electrode would be 0. So look at this. If I want to know the standard EMF of zinc Zn2 plus electrode, then that's what I will construct the cell, and that's what would be the idea by which I can measure the electrode potential of zinc 2 plus. Clear? Now let me tell you what is the thermodynamics of the cell reaction. We have just learned that in galvanic cell the chemical energy is converted into electrical energy. So the electrical energy is produced by the cell is equal to the product of the total charge of electrons and the EMF of the cell, which drives these electrons between the electrodes. If N is the number of moles of electrons exchanged between the oxidizing and reducing agent in the overall cell reaction, then the electrical energy produced by the cell is given below, equal to electrical energy equal to the charge of N mole electron. Now charge of 1 mole electron is taken as 1 farad. Now charge of N mole electron will be Nf, that is N times of 1 farad. So the total electrical energy I am getting here is Nf into E cell. Clear? So as we know that the charge of 1 electron is 1.6 into 10 to the power minus 19 coulomb. So charge of 1 mole electron will be equal to the Avogadro number into that value, which is exactly giving 96488 coulomb, and you can take it approximately 96500 coulomb. That is what equal to the 1 farad. So look at this. This is a picture in which we will get an idea about how does electrical energy and chemical energy are related with each other. So as I said that energy is used to do the electrical work, therefore the maximum work that can be obtained from a galvanic cell is called the minus NFE. So this is nothing but the delta G. So that's why I could say that delta G is equal to the minus NFE. So as we know from the thermodynamics, for a spontaneous reaction, delta G should be negative. So similarly, for a spontaneous cell reaction, I would say that E cell should be positive. Similarly, for a non-spontaneous reaction, delta G should be positive. Similarly, for a non-spontaneous reaction, E cell should be negative. And for the same reason, in equilibrium, delta G should be 0. So E naught cell should be also 0. E cell will be also 0. So similarly, if I take that particular formula or relation, whatever you can say, in standard state means at 298 Kelvin and 1 atmospheric pressure, then I would say that delta G naught, that naught stands for the standard. Delta G naught means it is standard gives free energy change, equal to minus NF E cell naught. So that means we know that standard free energy change is related to the equilibrium constant as per the following expression also. So here comes another thing, that delta G naught, standard gives free energy change, is also related to the equilibrium constant KEQ, that is minus RT ln KEQ. So I can also write another form of that particular formula, that is NF E naught cell equal to RT ln KEQ. So E naught cell from this equation becomes 2.3 RT by NF into log EQ. So this is where exactly the Nernst equations are starting its journey. Nernst equations is nothing but the equation of equilibrium constant, reaction quotient with the electrode potential. So this is the derivation. Derivation is not there in your syllabus, but still I am showing to you. But let me tell you what exactly the last formula of the non-stick question. The non